So the next section tells us that we can use the chain rule in reverse, and we kind of did this already with some simpler examples, but with more complex expressions. We can use the chain rule in reverse to help us with integrating trickier and more complicated expressions. So I just want to start by first of all reminding you that the chain rule is, if I want a function to be differentiated, then I can do dy by du multiplied by du by dx, where y is a function of u and u is another function of x. So I've got three examples here. They're all natural log functions, and you'll see why that is in just a second. But I would suggest you pause the video and have a go at differentiating these three functions for yourself, and then hit play, and I'm going to go through each of them, and we'll just double check that you remember all this and you're doing everything in the right way. Okay, so the first one, y is natural log of 2x plus 5, so u is 2x plus 5, so dy by du equals, well, this is y equals ln u, so it's just 1 over u, and du by dx is 2, differentiating 2x plus 5 gives us 2. So dy by dx is just 2 lots of 1 over u, which is 2x plus 5. Or we could just write this as 2 over 2x plus 5. Not super difficult. The second one, y equals ln of 4x squared plus 3x. This time u is 4x squared plus 3x. Dy by du is going to be exactly the same. It's still going to be 1 over u. Du by dx this time is going to be 8x plus 3. Just need to differentiate that, 4x squared plus 3x. So dy by dx should be 8x plus 3 multiplied by 1 over u. So we just end it with 8x plus 3 over 4x squared plus 3x. And then the final one, we have the same thing as natural log of a function. So our u is 7 plus cos x. Dy by du will still be 1 over u because it's still just y equals ln u. So this time du by dx is going to be, well, differentiating 7 disappears it. Differentiating cos gives us minus sine x. So dy by dx is going to be minus sine x over 7 plus cos x. The denominator is not going to change. So you can see there's a real clear pattern here. The natural log things end up as a fraction where the numerator is the derivative of the denominator. And hopefully we remember that from tackling this stuff earlier in the year when we did differentiation. But we can use that information to have a look at more complicated integration questions. So example 8 asks us to integrate 2x over x squared plus 1. And what we need to notice is that if I have my u is x squared plus 1, then du by dx is indeed the numerator, 2x. So I have this situation where the numerator is the derivative of the denominator. And what that means is this is probably the answer to an integration of ln x squared plus 1. Now, just like when we were looking at reverse chain rule before, what we kind of have to say is, well, I think it's this, but there may be some constants involved that I'm not certain are right. So I kind of need to say, well, imagine y is this, what's dy by dx? And then I need to check that matches the integration question. So in this case, dy by dx is going to be the derivative of this, 2x, over this, x squared plus 1, and that exactly matches my integration. So the answer to my part A integration is the integral of 2x over x squared plus 1 dx is just ln of x squared plus 1. But we also need this constant of integration just in case. Okay, part B, I have cos x and in the numerator and 3 plus 2 sin x in the denominator. So sin x does differentiate to cos x, so they look similar, but they're not quite exactly the same this time. So what I'm going to do is I'm going to start with, well, let's imagine that y equals ln of my denominator, 3 plus 2 sin x. In that case, dy by dx would be derivative of this, the 3 is going to disappear, differentiating 2 sin x is going to give us 2 cos x over the original, 3 plus 2 sin x. So this isn't quite right, because now I have this factor of 2 in here, which I don't have here. So what I need to do to adjust is I need to make this half the size, which makes my derivative half the size, and then we're exactly where we want to be. And that means that the integral of cos x over 3 plus 2 sin x with respect to x is half ln 3 plus 2 sin x, again plus some constant of integration. And all I've done is I've looked at the chain rule in reverse. I've recognized the numerator looks like the derivative of the denominator, and therefore I can probably use the chain rule to sort it out. So in general, if we notice that the numerator looks like the derivative of the denominator in a fraction, there may be some constant involved, but I don't care about that constant. I just need to try out ln of the denominator and then adjust for the constant. Okay, and we can use a similar method for generally using the chain rule, which we'll have a look at in the next video.